the fundamental idea here to make these recursive procedures efficient is that some calls are tail calls and some aren't. It's a distinction that figures out whether, when one procedure is calling another procedure, is there more work to do when that called procedure is finished or not. If there isn't anything else to do besides just return the value of the expression you call, well then that's a tail call. So tail calls have kind of a long definition. So let's go through it. A procedure call that has not yet returned is active, meaning we're still going to return something from it someday. Some procedure calls are tail calls. A scheme interpreter should support an unbounded number, that means as many as we want, an unbounded number of tail calls using only a constant amount of space. And it's going to do that by skipping over all those extra frames that you saw in the environment diagram that shows up in Python. Okay, so what's a tail call? A tail call is a call expression in a tail context. What's a tail context? Well, there's several. One is the last body sub-expression in a lambda expression. So it turns out that a lambda expression can have multiple different body expressions. The last one is the one that determines the return value. And so that expression is in a tail context, meaning it's a description of the last thing that this procedure is going to do before it returns. Now, in addition, you can also have a tail call as sub-expression 2 or 3 in a tail context if expression. So remember, an if expression has 3 sub-expressions: the predicate, the consequent, and the alternative. Those consequent and alternatives are tail contexts if it's the case that the whole if expression is in a tail context. So let's look at this factorial definition. The last body sub-expression in the definition of factorial is this whole thing, which is an if expression. So this if expression is in a tail context, which means that its sub-expressions 2 and 3 are also in a tail context. That's this k here, and then this call to factorial here. So that's a tail context as well, and this is a call expression in a tail context, and so it's a tail call. So that's the kind of thing that should only require a constant amount of space, no matter how many times we call it over and over again. The idea is, once you compute factorial of n minus 1 and k times n, you've already done all the work you need to do for factorial nk. All you have to do is return it. So it doesn't really matter what n and k are anymore once you've done all this work. Now there are other tail contexts. So all non-predicate sub-expressions in a tail context: cond, which you'll read about in your project, the last sub-expression in a tail context and or, and the last sub-expression in a tail context begin. These aren't terribly important, except that if you're actually sitting down and writing a scheme program, you need to know what the tail contexts are, so you know what's going to be the space efficiency or space usage of your program. So people spend a lot of time making sure that they put all of their recursive calls in tail contexts when possible, so that their whole program doesn't use too much space. But for today, we're just going to focus on these first two cases: last body sub-expression in a lambda expression, or sub-expressions 2 and 3 in a tail context if expression. So we've seen both of these examples right here. Let's do another example: computing the length of a list. A call expression is not a tail call if more computation is required in the calling procedure. So if after I finish my recursive call, I still need to combine that value with something else, then I don't have a tail call. But it's the case that linear recursive procedures can often be rewritten to use tail calls. So here's a linear recursive procedure for computing the length of a list S. And it says, if S is null, it's 0, otherwise it's 1 more than the length of the rest of S. Now, this is a tail context, because it's the last expression in length. Since it's a tail context and it's an if expression, both 0 and the alternative here are both in tail context. So this is good. This is a call expression in a tail context. So this addition is a tail call. However, this is not. So this is a call expression within a call expression, and that's exactly when you know you're not in a tail context. After we compute the length of the rest of S, we still have more work to do to add 1 to it. Now, we don't know what work there might be to do left, and so, for instance, maybe there would be a reference to S, and so we might need the environment for this function call around because there's more work to do. So in this case, an implementation of length here would require linear space to keep around all the frames for length in each recursive call. But let's see if we can rewrite length so that it is tail recursive. Here's a common way to do so. We define another procedure, length iter, which takes in the same list that we're computing the length of, and also the length that we've computed so far, n. If s is null, then we've computed the entire length, and we return n. Otherwise, we return the value of recursive call on the rest of s with 1 more than the length of what we've seen so far. So in the beginning, we haven't seen any length, so we start with 0. Each time we make a recursive call, we add 1 until we get to the end, and then we've computed the length. Now this is a very different program in terms of its behavior. This is in a tail context because it's the last expression in a lambda expression or a define. Why do I keep calling it a lambda expression? Well, a define of a procedure is implicitly a lambda expression. Remember, this is the same as saying define length tail, lambda s, blah, blah, blah. Okay. So that's in a tail context. This is in a tail context because this is a separate procedure definition, and this is the last thing in the procedure definition. Which means this is in a tail context, because when you have an if expression in a tail context, then its alternative is also a tail context. And that's a call expression in a tail context, meaning it's a tail call. Meaning this whole thing is only going to run in constant space. Now the actual list itself takes up linear space, but the additional space that's used in order to compute the length doesn't have a whole bunch of frames in it. It only has 1. So here this recursive call is a tail call, whereas this recursive call was not. So how do I convince you that this really matters? Well, we're going to have to run a demonstration. So it should be that the return value of the tail call is the return value of the current procedure call, meaning we can skip keeping around all the frames that we don't need, because the return values for the last frame can return straight up to the original call. Tail calls shouldn't increase the environment size. And we can see that by calling this factorial function on a big input. Okay, so here's scheme.py, which is part of your project. And way down below where you implement the extra credit, it says uncomment the following line to apply tail call optimization. So right now it's commented out, as you can see, which means we're using just a regular scheme eval, which is not optimized for tail calls because we haven't implemented that part yet. That's the extra credit. Okay, so let's define a function that returns n factorial times k. Define factorial of n and k if n is 0, we just return k. Otherwise, we'll return factorial of n minus 1 and k times n. Okay, so what sort of state are we in? We have a tail recursive function. We analyzed that already. This is a tail context, so this is a tail context. We have an interpreter that is not optimized for tail calls. So it's just going to create a frame every time we make a recursive call, and that frame will stick around until we return from the call. And that will use a linear amount of space, which means that if we run scheme.py and load in this factorial, we can compute the factorial of 10. We can compute the factorial of 100. But if we compute the factorial of 1000, we reach an error. It says maximum recursion depth exceeded while calling a Python object. So what happened? It got all the way up, it seems, to computing the factorial of 673, and then it just gave up because it had made too many recursive calls, and so it was using up too much memory. So Python said, sorry, you've reached your limit. We're done. Which is unfortunate, because we should be able to compute as much of this as we want, using a constant amount of space. So I have an implementation of the extra credit, which just says use a different eval function, one that doesn't create an extra frame when it doesn't need to. So let's run this again. Let's load our factorial function. If I compute the factorial of 10, it works fine. 100 works fine. 1000 works fine as well. And if I compute the factorial of 10,000, well, sure, it takes a while. I'm not making anything really faster, but I am saving the extra space. So we computed this huge number, 10,000 factorial. Now, eventually this program will run out of space, not because we create extra frames, but because representing this number will just become too big because it has so many digits. But that's going to take a long while. So very efficiently, we've computed factorial of 10,000 using tail recursion to make sure that we don't use any space that we don't need to use.